A challenging problem for students to solve is one that involves two objects that are moving simultaneously. A good example of that might be a problem that says a speeder traveling at 35 meters per second passes a police officer who immediately gives chase by accelerating at 3 meters per second until he catches him. And typical questions might be, how long did it take the police officer to catch the speeder, and how fast was the police officer going when he caught him? Well, to solve a problem like that, there's a couple key things to remember. One is, you can assume that if they're moving together, they share the same time interval. Clock is ticking for both of them, so time would be the same. And in this case, there's a moment when the two objects are together, and so at that second, they share the same final position. Now, you can take advantage of these two facts by creating equations, which you already know how to do, and then setting those equations equal to each other, and then solving for one variable or another. Okay, in order to solve this problem, let's write down everything we know. This side will be for the speeder, and this side over here will be for the police officer. So the speeder's initial speed was 35 meters per second. He was not accelerating. His initial position was 0. We don't know his final position. We don't know how long it's going to take to get caught, and of course his final velocity was the same as his initial. For the police officer, his initial velocity is 0. His acceleration was 3 meters per second. His initial position was 0. Again, we do not know his final position, nor the time it takes, nor how fast he was going. Now that we've established the givens and the unknowns, let's find the right equations. For the speeder, really the only thing we can say is that his final position would be equal to 35t. That's just a really shortened version of the quadratic formula with all the zeros. It just shortens to that. For the police officer, his final position would be equal to 0 initial position. VIT would be 0, so all he has left is 1/2 times 3 t squared. So we have two equations, one for each, one for the speeder, one for the police officer. And of course the key is that we can set these equal to each other, because when the police officer catches him, they will be at the same position. So we can set 35t equal to 1.5 t squared, and the t divides away, so we take 35 and divide it by 1.5, and we get 23.3 seconds is the time. So it will take the police officer 23.3 seconds to catch up to the speeder, and so that answers question A. Alright, question B. How fast was the police officer going when he caught the speeder? Well, now we can take advantage of the fact that we know more information. We now know that the time was 23.3 seconds, and so now we can use this formula, final velocity equals initial velocity plus AT. So his final velocity will be 0 plus 3 times 23.3, which is 69.9 meters per second, which you'll notice is about twice as fast as the speeder was going. So the police officer really has to get up to a much higher rate of speed in order to catch him. And so that's really the algebraic way of doing it. There's also another way to do it. Could have been this. You could do it graphically. So I'll just show you this here real quick. Let's suppose we have a position time graph, and for the speeder, he would start at about start at 0, and he would travel at a speed with a slope of 35. The police officer, starting from the same place, would have to accelerate, and he eventually would have a path like this, and right here would be the position, and here would be the time. And so if you have a graphing calculator, you could have put these two functions in right here, put it one in x1 and one in x2, and graph them simultaneously, and then you could have found the intersection of these two functions, and that would also have given you the answer.